We've been discussing colligative properties so far, and our final colligative property we'll discuss is osmosis. Now, osmosis is referring to the flow of a solvent through a semi-permeable membrane. The solvent flows as a result of a difference in particle concentration or osmotic pressure, which are connected to one another. When we talk about particle concentration, we can refer to that as the osmolarity, which we can abbreviate OSM. And that is equal to the molarity times our I value. So this should be a lowercase I. It's our molarity times our Van Hoff factor. Our osmotic pressure is the pressure that's being created as a result of that difference in concentration. And that osmotic pressure we represent with the Greek letter pi. And it's going to be equal to our I value, so our Van Hoff factor, times our molarity times R times T. So capital M in both cases, that's our molar concentration of molarity. I is our Van Hoff factor. R is our ideal gas constant. It's 0.0821 liters times atmospheres over moles times Kelvin. And T is our temperature in Kelvin. Now, when it comes to osmosis, we said that's going to be the flow of a solvent through a semi-permeable membrane. The solvent will always move from the side with the low osmolarity or the low osmotic pressure to the side with the high osmotic pressure or osmolarity. Now, it is doing this in an attempt to equalize the concentrations or pressures on both sides of that membrane. The solvent will flow until the concentrations or pressures become equal. As the solvent flows, the concentrations are going to change. The side the solvent leaves will become more concentrated. The side that the solvent enters becomes less concentrated. So over time, they're going to eventually become equal. So in our image here, we can see a starting situation. So we've got this tube that has got a membrane in the center, and it's separated on each side with solutions. One side is just water molecules, which we see in the red and white models. And then we've got the other side contains solute particles. So what's going to happen is the water, the solvent, will flow through the membrane. It's going to flow from the side with less solute to the side with more solute towards the higher concentration, the higher pressure, in order to try to dilute that side so that, again, both sides eventually become equal. So one of the things we want to be able to do with osmosis is predict how our solvent might flow. So if we look at an example, we've got a 2 molar aluminum nitrate solution. It's separated by a semi-permeable membrane from a 3 molar potassium chloride solution. And we're asked in which direction is our solvent going to flow. So we have a 2 molar aluminum nitrate solution. We see this double line here. That double line is representing the membrane. So that's just telling us we've got this 2 molar solution separated by a membrane from the 3 molar solution. Now, when we look at this, we can't judge the direction based on molarity. The direction depends on the specific particle concentrations or pressures. It depends on if something's an electrolyte or an non-electrolyte. And based on this, we've got to determine either our osmolarity or our osmotic pressure. We can judge direction of flow from both. So if we look at our aluminum nitrate, we see that aluminum present. The aluminum right away lets us know that we are dealing with an ionic compound. Now, since it's an ionic compound, that aluminum nitrate is an electrolyte. When it dissolves in water, it breaks into Al3 plus and 3 NO3 minus. So I have 1 aluminum plus 3 nitrates. That produces 4 moles of ions in my solution. Now from there, we can determine either our osmolarity or our osmotic pressure. So the osmolarity would be the concentration, which was 2 molar, times my I value. So 2 is the molarity, 4 is the I value. So we're getting an osmolarity of 8. My osmotic pressure is, we start off the same way. It's the molarity times the I value, but we're going to add in the R value and our temperature. Now we're going to assume that we are at standard temperature, which is 298 Kelvin. We always assume that if we're not told a specific temperature. And this would give us an osmotic pressure of 180 atmospheres. Now we're comparing this to the other side of our membrane. The other side of our membrane, we have a potassium chloride solution. We've got that potassium metal. It's an ionic compound. So again, this is an electrolyte. When the potassium chloride dissolves in water, we're going to get K plus and Cl minus, producing 2 moles of ions in solution. So our osmolarity would be the 3 molar times 2 to give us an osmolarity of 6. Or again, we could determine our osmotic pressure. That's going to be the 3 molar times the I value of 2 times R 0.0821 times 298 Kelvin, giving us 150 atmospheres. So when we're looking at the direction of flow, solvent is going to flow from the side with the lower concentration, the lower pressure, towards the side with the higher concentration, the higher pressure, and it's flowing towards that side in order to bring the concentration down to dilute it, which in turn decreases the pressure. So in this case, the solvent is going to flow from the potassium chloride and into the aluminum nitrate solution. The solvent flows from lower osmolarity or osmotic pressure to higher. Because the aluminum nitrate produces more particles in solution, it results in a higher osmolarity than the potassium chloride. So what we're going to see happen over time is that the concentration of the potassium chloride as water leaves it, its concentration goes up as its volume goes down. Water is going to enter the side with the aluminum nitrate. Its volume is going to go up, causing its concentration to go down. And again, this continues until they become equal, or we continue to see that change. Once it actually becomes equal, then we're going to reach an equilibrium. We're going to still have solvent flow, but the rate is going to be the same. Water will flow back and forth each side, but we're not going to see concentration or volume changes. Now we see a few important applications of osmosis. In a laboratory, we might use it to purify samples. It's very importantly used in things like dialysis, so purification of our blood when our kidney stops working. We can use it in preservations of fruits and meats. So for example, if you want to make pickles, you can start off with a cucumber. You're going to place that cucumber into a very, very salty solution so that the outside concentration, the outside osmotic pressure is much higher than what's inside that cucumber. What happens is that the water inside the cucumber leaves towards the higher concentration salt on the outside in order to dilute that salt. The result is that your cucumber shrinks and you get that pickle. We also get movement of water into and out of our cells based on concentration differences. This is all osmosis. So looking at a couple of problems. We want to make sure that we can calculate our osmolarities and osmotic pressures for given solutions. So if we look at a 0.5 molar solution of K2SO4, that K2SO4, that is an electrolyte. It's ionic. It breaks into 2 potassium cations and a sulfate anion. So 2 cations, 1 anion. My I value is 3. So if I am calculating my osmolarity, that is my molarity times my I value, giving me an osmolarity of 1.5 OSM. If instead we were asked for the osmotic pressure, the osmotic pressure is my molarity times my I value times R. We're not given temperature, so again, we're going to assume a standard temperature of 298 Kelvin, which gives me an osmotic pressure of 36.6 atmospheres. Looking at our next problem, we've got a 0.65 molar solution of iron chloride. Iron is a metal, making this an ionic compound, making this an electrolyte. The iron 3 chloride is going to break into iron 3 plus. That subscript on the chlorine means there are 3 Cl minuses. So 1 iron plus 3 chlorides gives me 4 particles, so my I value is 4. So my osmolarity is going to be my molarity, 0.65 times I of 4, which gives me 2.6 OSM. My osmotic pressure would be 0.65 times 4 times 0.0821 times 298 Kelvin, giving me a pressure of 63.6 atmospheres. And then finally, I've got this 1.5 molar solution of CH3OH. There's no metals here, so it's not ionic, it's molecular, it's an organic compound. Remember, we're going to classify this as an alcohol. We've got that OH group. Being molecular, this is a non-electrolyte. So as a non-electrolyte, it's not going to break into ions in solution. Its I value will just be 1. That means that my osmolarity is 1.5 times 1. So I have 1.5 OSM. And then my osmotic pressure would be 1.5 times 1 times 0.0821 times 298, giving me an osmotic pressure of 36.6 atmospheres. So larger concentrations we have, the greater the osmolarities, or not just concentrations, concentration plus the number of particles gives me higher osmolarity, higher osmotic pressure. So in our next problem, we're given a set of solutions and we're asked to indicate which direction our solvent would flow. And we're asked to explain this in terms of osmolarities. You could also be asked to explain it in terms of osmotic pressure. So we're doing the same thing we did in number 1. We've got to figure out, do we have electrolytes or non-electrolytes? And we've got to figure out if any of these are we've got to figure out our osmolarities. So CH3, CH2OH, all nonmetals. It's a molecular compound. It's a non-electrolyte. Its I value would be 1, and therefore its osmolarity is the same as its molarity. It's going to be 0.5. If I were to calculate my osmotic pressure, so I would be taking that 0.5 times R times my temperature of 298. So I'd have an osmotic pressure of 12.2 atmospheres. So that is on one side of my membrane. The other side of my membrane, I've got the calcium nitrate. Calcium's a metal. Right away, that makes this ionic. That makes this an electrolyte. I have 1 calcium plus 2 nitrates. It's going to give me an I value of 3. So my osmolarity is going to be my concentration of 0.4 times 3, which gives me 1.2 OSM. If I were to calculate my osmotic pressure, it would be the 1.2 times R times 298 Kelvin, giving me an osmotic pressure of 29.4 atmospheres. So when we're judging the direction of flow, we're comparing the osmolarity or the osmotic pressure. We can actually simplify this to the osmolarity because we're looking at the same temperature, and R is a constant, so temperature and R are constants, so those remain the same. So really it's the concentration and the I value that is impacting our flow direction. But looking at these, my concentration is going to flow from the side with the, or my solution, solvent, will flow from the low side to the high side. So I'm comparing a 1.2 osmolarity to a 0.5. That means that my concentration is going to flow from the 0.5 molar CH3CH2OH and towards the calcium nitrate. And that is because the calcium nitrate has the higher concentration, the higher pressure. The solvent will flow in and dilute it, which will bring that pressure and concentration down. So looking at our final problem here, I've got a 0.2 molar aluminum sulfate solution separated from a 0.2 molar sodium chloride solution. Aluminum sulfate has aluminum, which is a metal that makes this ionic and an electrolyte. So I can look at my subscripts and determine, I could break it apart, but I could also look at my subscripts. This means I need 2 aluminums, 3 sulfates. 2 plus 3 gives me an I value of 5. So my osmolarity is going to be 0.2 times 5, which is 1 OSM. My sodium chloride, it is also an electrolyte. 1 sodium plus 1 chloride gives me 2 particles, so my I value is 2. So my osmolarity is going to be 0.2 times 2, give me 0.4. So when I look at my direction of flow, again, we're going to flow from the side with the lower concentration towards the higher concentration. The sodium chloride has the lower particle concentration. So we're flowing from the sodium chloride towards the aluminum sulfate. And again, that's because we're going to flow, same reason as above, flows from low to high. So if we just looked at the molarities, these two are equal. But because of the number of particles they produce, the concentration of ions is not actually equal. The aluminum sulfate has the higher ion concentration. It's going to create that osmotic pressure, so solvent's going to flow to equalize them. Now we saw with a previous colligative property with our freezing point depression that we could use that freezing point depression in order to determine molar mass of an unknown. Osmotic pressure can be used the same way. You have an example exercise in your textbook, 11.3. I would encourage you guys to take a look at that.